For this lesson, we're going to be taking a look at a type of multiplication that we can do with vectors, and that's known as the dot product. And in particular, for this lesson, we're going to be focusing on the dot product in terms of geometric vectors. And by geometric vectors, that means we're going to be using geometry, meaning diagrams, and we're going to be talking about the angles, that sort of thing. In an upcoming lesson, we're going to look at the dot product in terms of what are known as algebraic vectors, so algebraic expressions. But for now, we're going to be focusing on geometry. And so we're going to be talking a lot about the angles, for example. This type of vector multiplication, we've talked about the idea of adding and subtracting vectors. We've talked about the idea of multiplying a vector by a scalar quantity, which is just by a number. But what happens when we have two vectors and we want to perform some form of multiplication? The dot product is one way to do that. And the interesting thing about the dot product is the result is a scalar. So you take two vectors and then you perform this operation called a dot product, then you actually end up with a scalar, which is just a number. The notation I'm showing here, first of all, when you read this, you would just read this as a dot b, or you might read this as vector a dot vector b, but normally they just read that as a dot b. Because it's understood to be a vector operation, we know a dot b must include vector a and must include vector b. The way you determine that is you take the magnitude or the absolute value of a and the magnitude of b, and you multiply that by the cosine of the angle between them. And that angle is always going to be between 0 and 180. And you might ask, well, hold on, why can't that be an angle between 0 and 360? And the answer to that is, even if I have a situation like this, where you might say, well, I want that to be my angle, but the angle between them is the shortest angle between them. So it would still be theta would be here rather than going all the way around. And so once again, we'd have an angle between 0 and 180. Now, some interesting results that we get from the dot product, which is if we have an acute angle, so if the angle between the two vectors is between 0 and 90 degrees, then we know from the cast rule, cosine, that's going to be a cosine in quadrant 1. So that tells us that cosine is going to be positive, but we know that the magnitude of A and the magnitude of B are always positive. So when we take our dot product and we say that A dot B is equal to magnitude of A, magnitude of B, cosine of theta, this is going to be positive, this is going to be positive, and in this case, cosine of theta will be positive, which means for an acute angle, the dot product is always going to be positive. You can reverse that, which means if you are able to take a dot product and you end up with a positive result, you know that there is an acute angle between the two vectors. And when I talk about the angle between two vectors, this is as good a time as any for me to point this out. When we talk about the angle between two vectors, that is when the vectors are arranged tail to tail. So this is not necessarily the arrangement I would use if I was doing a vector addition. Then I use tip to tail. But when we talk about how vectors relate to each other and the angles by which they relate to each other, that's always tail to tail. If, on the other hand, I have a 90-degree angle, if I have a right angle between my two vectors, then of course that means that angle theta is 90 degrees, but the cosine of 90 degrees is equal to 0. So now if I do A dot B, the magnitude of A is positive, the magnitude of B is positive, and so I have a positive and a positive multiplied by 0. So I end up with an overall result of 0. Now that is not particularly useful on its own. I guess it's a test for a right angle triangle, but the flip side is if you take the dot product and you get an answer of 0, you know you do have a right angle triangle. And then finally, you could probably predict we were going to go here, which is if we have an obtuse angle, so if our angle is between 90 and 180, then cast rule, between 90 and 180 puts us in quadrant 2, and we know that cosine is going to be negative there. But the magnitude of A and the magnitude of B continue to be positive, so that means that we end up with an overall negative result. And the corollary of that, which just means essentially, that means this is another result you can get from it if you work backwards, is that if I get a dot product that's negative, I know I have an obtuse angle. That's not always going to be useful, but it's something we can add to our bag of tricks when we're trying to do an analysis. Now, here are some of the properties of the dot product. The dot product is commutative. So regardless of the order that you perform the dot product, A dot B is the same as B dot A. It is distributive. This is a very interesting one. So the dot product, which is a vector multiplication, distributes the same way that a regular multiplication would distribute. So A dot of B plus C. Now you have to remember, this is a vector, and if we're going to take the dot product, that means that this bracket must be a vector as well. So it still has to be a vector dotted with another vector, and the only way for this bracket to be a vector would be for the pieces inside it to also be vectors. And I can then distribute this A into the B and this A into the C with a dot product on each of those distributions. If I take A dot A dot A, that's equal to the magnitude of A multiplied by the magnitude of A multiplied by the cos, but the angle between the exact same vector would be the cosine of 0 degrees. Well, the cosine of 0 degrees is simply equal to 1, so this works out to be the magnitude of A multiplied by the magnitude of A, which is the magnitude of A all squared. And then finally, the last property we'll look at is if I have one of my vectors being multiplied by a scalar, I can associate that scalar with either of the vectors. So first of all, I can say the scalar, instead of associating the scalar with A, the vector A, I could associate the scalar with the vector B. Or I could associate the scalar with the overall dot product once I'm done. So that's an associative property. That's what allows me to move this scalar around, and it's essentially I'm moving it around as a factor. So that's the associative property is something you make use of when you are doing factoring in algebra. Okay, we've been asked to show that the vectors A plus B dotted with the vector A minus B is equal to the magnitude of A all squared minus the magnitude of B all squared. As is the case if we think back to trigonometric proofs, we generally want to start with the more complicated looking side. And since this idea of dot product is newer to us, I'm going to suggest that that's the case. We're going to start with the left. And since I'm doing the video, you have no choice. We're going to do the left. So we have A plus B dotted with A minus B. We're going to use the distributive property, which means I'm going to distribute the same way I would. It's essentially what I'm going to do here is like doing FOIL. But I'm actually going to use the distributive property. So I'm going to do this in 2 steps, which is I'm going to take A and I'm going to distribute it onto this other bracket, which is A minus B. And then I've got plus B, and I'm going to distribute that with a dot product onto A minus B. And this is exactly when we did the binomial expansion in your quadratics unit in grade 10. This is the same sequence of steps that we would have taken. And now I'm going to distribute this A into this bracket. So I end up with A dot A, and that's going to be minus A dot B. And then I'm going to distribute this B dot A, and into the negative B, that's going to be minus B dot B. From our previous page, let's just go back to that page. If I have a vector dotted with itself, I just end up with the vector quantity all squared, the magnitude all squared. And I can make use of this commutative property, which is A dot B is the same as B dot A. The order that I write them doesn't matter. So this A dot A is the magnitude of A all squared minus A dot B. There's nothing more I can do with that for now. But plus B dot A is the same as plus A dot B. Now you wouldn't really need to show this normally, but I'm being very explicit in what I'm doing here. Minus B dot B all squared. And when I say you wouldn't normally need to show this, what I mean is these are the same except for one's positive and one's negative. So they add up to 0. They don't add up to the 0 vector. They add up to 0 because each of these on its own is a scalar. So don't make that mistake from a notation point of view. And so when I go ahead and clean this up, I end up with the magnitude of A all squared minus the magnitude of B all squared. And left side is equal to the right side as requested. I've got two vectors, u and v, and I've been asked to find the angle between these vectors given a couple of pieces of information. I've been given the fact that the magnitude of the vector u is 3 times as large as the magnitude of the vector v, and that the vector addition 3u plus v is perpendicular to the vector subtraction u minus 8 times v. And my goal here is to find the angle between them. So I need to find out a little bit of information about u and v. Now there's not much I can do with this point number 1, so I'm just going to leave that alone. Point number 2, on the other hand, actually that's quite interesting, because what does perpendicular tell us? Well, one of the things we talked about with perpendicular was that the dot product would be 0. That's one of the properties you get. So it's not going to be the dot product of u and v, it's going to be the dot product of 3u plus v dotted with u minus 8v has to be equal to 0. That's what it means for these to be perpendicular. And now I have formed an equation. So let's go ahead and distribute this. How you do this distribution, how comfortable you are to do this is up to you. But I'm going to take my time. So once again, I'm going to do it in one fewer step than I did last time. So I get 3u dotted with u. I'm actually going to use FOIL, just in case you're wondering. I'm going to use the same procedure that we would use for FOIL. So the first is 3u dotted with u. The outer is going to be 3u dotted with negative 8v. So what that does is I first just multiply the constants together and I end up with negative 24. And then I end up with u dotted with v. And then I do inner, which is going to be positive v dotted with u. So that's going to be plus v dot u. And then last is going to be positive v dotted with negative 8v, so that's going to be minus 8v dotted with v. And all of that is equal to 0. So 3u dot u is just 3 magnitude of u all squared. I've got minus 24u dot v, and I've got a v dot u here, but I'm just going to remind you that v dot u is the same as u dot v. And so I've got negative 24 of these plus one of them, which means I have minus 23 u dot v's. And I think I'm going to need to move this down a little bit because I put that extra green line in there. And then minus 8, and v dot v is the magnitude of v all squared, and that's equal to 0. Okay, so we're moving along here. Now remember, we don't actually know these numbers. And the other thing to do is keep in mind our goal, which is the angle. I'm going to write one more line, and that will hopefully give you enough idea watching this as to where you'd like to go yourself. Ideally, I'd like you to be working through this exercise on your own, pausing the video, trying it on your own, and then trying to do it yourself. So this is going to be minus 23, the magnitude of u, times the magnitude of v, times the cosine of the angle between them. That's good news because we're interested in the cosine of, or we're interested in the angle between them, minus 8 times the magnitude of v all squared, and that's equal to 0. Now I've still got the magnitude of u and the magnitude of v, but now we can make use of our piece of information number 1, which is that I know the magnitude of u is actually 3 times the magnitude of v. So that means the magnitude, I've got 3, and the magnitude of u is 3 magnitude v, which means the magnitude of u all squared would be 3 magnitude of v all squared minus 23. The magnitude of u I'm going to replace with 3 times the magnitude of v multiplied by the magnitude of v times the cosine of theta minus 8 times the magnitude of v all squared. And it wouldn't be worthwhile having this conversation without being able to make the assumption that the magnitude of u is non-zero and the magnitude of v is non-zero. Otherwise, why are we even looking at these vectors? And none of these other properties would make sense. This statement about perpendicularity wouldn't make sense. So for that reason, maybe you'll notice that I've got a magnitude of v squared here. A magnitude v is a magnitude v squared, magnitude v squared. So I'm actually going to take everything and I'm going to divide by the magnitude of v all squared. You could also think of this as factoring out the magnitude of v all squared, but we know the magnitude of v can't be 0. And so it's safe to divide by the magnitude of v all squared because we know the magnitude of v is non-zero. So I go ahead and do that, and then I end up with, now you got to be careful, I don't want you rushing through this. I'm only dividing out by the magnitude of v all squared, but I still have 3 here, and then 3 squared is equal to 9, so I still have to keep that. Minus 23, and this 3 is still here, and then we still got our cosine theta, minus, and that 8 is still there, but we've divided through by v squared, so we end up with that is equal to 0. And now I can start to do some cleanup. 3 times 9 is 27, minus 8 is equal to 19, minus 23 times 3 is 69 cosine theta, and that's equal to 0. And so I end up with 19 is equal to the cosine, not the cosine, is equal to 69 cosine theta, which means that cosine of theta is equal to 19 over 69, and theta is equal to the inverse cosine of that fraction, and that works out to be the inverse cosine of 19 divided by 69, and that is equal to approximately 74.0 degrees. Therefore, just make sure the angle between u and v. Therefore, the angle between vector u and vector v is 74.0 degrees. And that's it for this lesson, taking our first look, not our only look, but our first of 2 looks at the dot product.